Hello calculus fans, and welcome to section 2.6 where we talk about limits at infinity and horizontal asymptotes. In section 2.2 we investigated infinite limits and vertical asymptotes. There we let x approach a number, and the result was that the values of y became arbitrarily large, positive or negative. In this section, we let x become arbitrarily large, positive or negative, and see what happens to y. So let's look at example 1. Now notice that this is infinite limits, and sometimes these they're easy to get these two ideas confused, but what we're doing today is limits at infinity. What we did previously was infinite limits. So infinite limits, these were from section 2.2. So we handled these previously. This is section 2.2. And these were problems like this one, the limit as x approaches 0 of 1 over x squared. And we learned that we could make this 1 over x squared be as large as we want just by letting x get close enough to 0. So that we would say that the answer to this is infinity. And we said really that means the limit doesn't exist because it doesn't equal a number L. And also that we could make this expression be as large as we want just by letting x go to 0. So this is an infinite limit. And then we had other ones like this where we take the natural log function, we let x approach 0. And of course the natural log function as the graph of the natural log looks like this. So as x approaches 0 from the right, so x is coming in here approaching 0 from the right, and as that happens, natural log of x is heading down towards negative infinity. So this answer would be negative infinity. So these were infinite limits. The limits are infinite, right? The limit of this is infinite. The limit of this goes to negative infinity. So these were infinite limits. And then the note here, what we did here is we let x approach a number. So x is approaching a number, right? So in this case it's approaching 0. Over here it's approaching 0 from the right. So we let x approach a number, and then f of x approached infinity or negative infinity. So these are infinite limits. But what we're going to switch to now for section 2.6 is we're not going to work with infinite limits, we're going to work with limits at infinity. So now we're going to let x approach infinity. So let's take a look at this function. We've got a expression f of x is x to the fourth minus 5 over x to the fourth plus 2. And we want to look at what happens to this expression as x becomes really large, positive or negative. So in other words, we could think of it as if we take the limit of this expression as x approaches infinity or negative infinity. So if you put this one in your graphing calculator, put this in for y1 equals this, and you graph it, you'll see it does something like this. Around the origin it dips down, and then it appears as you go out, if you use your trace, on the calculator, you can trace out to the right or to the left. And it looks like the graph of this function gets closer and closer and closer to 1. It looks like you can make it go as close to 1 as you want to by going way out to the right or way out to the left. So let's take a look also at a table in the calculator. So I'll say number 2, let's just say a table. And if we again plug this into y1 and then use the table, and I'm going to enter some large numbers, large positive and large negative, and let's just see what happens. We go to our calculator and we go to y equals, and we'll put x to the fourth minus 5 divided by x to the fourth plus 2. Then I'm just going to go to a table. So above the graph it says table, so I go second table. And now I've got some things in here so I can delete these. But if you try to delete things and they don't delete and you just have a whole bunch of numbers that scroll, there's a easy fix. You have to go to table set. So if that's happening, go to second window to get to the table set. Just make sure the independent variable is on ask. You want it to look like this, ask and auto, and then it should work. So I have to go back to the table, and then I can plug in some values. So I want to put like 50, and it says 1, but if I go over and put the cursor on the 1, it shows this. So you can see it's real close to 1, but it's rounding. So it'll round here, but if you want to get more decimal places, you go over to there. So let's say if I go to 100, again it will show 1 here, but if I select the 1, see it's closer to 1 now. See, when I go to 100, it gets closer to 1, and it's going to get closer and closer, as it looks like from the graph also. And negatives work too. So if I go negative, 50, it's close to 1 there too. So I guess we can look at the graph. So if I go, let's go zoom 6 to put it in standard window, and it looks like that. And then, as I mentioned earlier, if you use a trace key, so if I go trace, and then if you happen, if you want to go further and further and further out, you can see the Y value will get closer and closer and closer to 1. So the note here, then, what we did is we let x approach infinity. This is what we're going to do. We're going to let x values approach infinity or negative infinity, and we see what happens to f of x. So we're going to let x approach infinity, and then we're going to see what happens to f of x, or whatever our function is. So over here we've got the limit as x approaches infinity of this expression, which we just looked at. And so this is a limit at infinity. The limit is approaching infinity, and it looks like this is equal to 1. We don't know that for sure yet. I mean, we're guessing, but we turn out to be right in this case, which we'll see later. And also, here we've got x approaching negative infinity of the expression, which also equals 1. So the note here says this: the limit as x approaches infinity of f of x equals L means that the values of f of x become closer and closer and closer to L as x approaches infinity. And one other thing will happen also. So L will be a number, and then also L turns out to be the horizontal asymptote of the graph. So whatever this number is, we'll see it ends up being a horizontal asymptote. So let's look at another example here. Example 3 says, consider the function f of x equals 1 over x. In this one, we've seen this graph in plenty of classes before. It's basically this graph that does this, and it will go something like this. Right, everyone's seen this graph a bunch of times. So the limit as x approaches infinity of 1 over x equals, what you can see is x gets really big. If I'm going way out here, I'm going to have 1 over a huge number, which means this expression is going to 0, and it's reflected in the graph here. So by taking x large enough, we can make 1 over x as close to 0 as we please. Therefore, the limit as x approaches infinity of 1 over x equals 0. And intuitively, you can see it. If I'm taking the limit of this expression and I just make x be bigger and bigger and bigger, just think like 1 divided by 1 billion is really tiny. 1 divided by 1 trillion, even more tiny. And you can basically make this thing as close to 0 as you want by making x big enough. So someone said, can you make 1 over x to be within 1 trillionth of 0? You could, right? Just by making x big enough. So what we're expressing here is that the limit of this expression 1 over x as x approaches infinity is equal to 0. So let's take a look at a couple definitions. Definition 1 says, let f of x be a function defined on some interval from a to infinity. Then the limit, as x approaches infinity, of f of x equals L, means that the values of the function can be made arbitrarily close to L. And we've learned before that arbitrarily close just means as close as we want, right? As close as we want. So we can make the function as close as we want to L by taking x sufficiently large. We can make this function as close to that as we want, within a trillionth of that, as long as you take x large enough. And then we've got another definition, definition 2. Let f of x be a function defined in some interval from negative infinity to a. And in both these cases, a is just some constant, some number. Then the limit as x approaches negative infinity of f of x equals L means that the values of the function f of x can be made arbitrarily close, again, arbitrarily close to L, by taking x to be sufficiently large negative. And in either of the cases, the line y equals L is a horizontal asymptote of the curve. Now we have to be careful about this, okay? This is a line, right? It's a line, it's not a number. So the asymptote is never going to be 3. The asymptote is going to be a line y equals 3, right? So we have to be, remember, details matter. And the higher you go in math, the more details are going to matter. So we want to make sure we understand this. A horizontal asymptote is not a number. It is not a number. It is a line, right? A horizontal line. It's not a number. It's a line. So we need to make it look like a line y equals L. Just make this more clear. It sounds really picky, but a horizontal asymptote is not only a line, it's a horizontal line. So our answer to the question, what is a horizontal asymptote, will always look like y equals something. So it could look like, so let's say you're working on something and they say horizontal asymptote. You can't say like horizontal asymptote equals 3. That doesn't make any sense. You can't say horizontal asymptote is x equals 3 because that's a vertical line, right? So you don't want any of this. You want to say something like the horizontal asymptote is the line y equals 3, right? This is a horizontal line, right? This is a horizontal line. X equals 3 is a vertical line, and 3 is just a number. So we need to be very, very specific in what we're saying. So if we're looking for horizontal asymptote, it'd be something like y equals 3, y equals negative 2/3, something like that, where it's a horizontal line. There's a little another note here. So let's say you go through here and you take the limit as x approaches infinity of this function, you get some real number L. Or you take the limit as x approaches negative infinity of some function, you get this real number L. So in that case, this number L, that number is actually part of a horizontal asymptote. So if you get a limit of L, that means the line y equals L, again, it's a line, remember? It's a line, y equals L, is a horizontal asymptote of the graph of y equals f of x. Then we get a theorem here. The theorem says if r greater than 0, so r is a positive number, is a rational number, then the limit as x approaches infinity of 1 over x to the r equals, this one is not really tricky. Just think if r were 2, 1 over x squared, as x gets bigger and bigger and bigger, 1 over x squared is going to be closer and closer to 0, so the limiting value is 0. But just do a quick review here. So rational numbers. Okay, so you start off, number systems. The most basic number systems are the natural numbers, sometimes abbreviated with a scripted n. Sometimes they're called the counting numbers. So the natural numbers are the counting numbers. These are things that just you develop naturally when you're a kid and you start counting. Usually the first number you learn is 1, right? It's not like negative 2/3. It's usually 1. Or when societies start developing number systems. Usually the first number that gets developed is the number 1. So natural numbers are things like 1, 2, 3, and on to infinity. And then this bracket's a little bit messed up, but it's supposed to be a bracket there. And then usually you add something in here. So usually you'll add in the next thing that comes along in the development of a number system is usually a 0. Which you really need. You need to have a 0 or you can't have a very well-developed number system. Like the Roman numerals don't have a 0. So try to multiply Roman numerals together. Try to come up with some easy way to multiply, let's say, 23 by, let's say, 13. Or let's just say 12. Try to multiply these together. There's not an easy way to do it, so you really need a 0. With the 0 added to the natural numbers, then we have the whole numbers. Then we have 0, 1, 2, 3. So it's just that one more number added to the natural numbers or the counting numbers to get the whole numbers. And then what's the next development along the way for the number system? What else could we have here? Negative numbers. So negative numbers, we usually have this little z, which represents a set here, which is the integers. Usually abbreviated z, which I think is from a German word Zehlen or something like that. It's been a while since I've heard it, but these are basically the whole numbers plus now negative numbers. So negative natural numbers. So now we have this. We have negative, well, actually, let's see. We're going to have negative 3, negative 2, negative 1, 0, 1, 2, 3. Right? So these go, they keep going back further negative here and then further positive here. So we've got the natural numbers or the counting numbers. We add a 0 to the whole numbers, add all the negatives to get the integers. And then what we do is we come up with the rational numbers. So the next step here is the rational numbers. These are numbers a lot of times abbreviated with the script Q. And rational numbers are just numbers that can be written A over B, where A and B are integers. Okay, so the rational numbers. So even like the number 7 is a rational number because you could write it 7 over 1. And you probably notice that whole numbers include all of these. Integers include all of these. Rationals include all these. So we keep building on the previous sets. Now, when it comes to the next spot, we stop here. There's the rational, and then there's the irrational. But they're different. So the irrational, they don't have their own little symbol. But the irrational basically are the numbers that cannot be written like this. You can't write an irrational number as A over B, where A and B are integers. So usually they just say something like cannot be written A over B, where A and B are integers. Okay, so those are the irrational. So there's sort of like a little break right here. There's where they build on each other, and then all of a sudden the irrational are none of these. All right. So we started out talking about the rational numbers, which is basically here, and anything that can be written as a fraction. But I just wanted to keep going since we're so close to almost having the real numbers. So the real numbers, if you group all of these together, the irrational and all the rational, then you get the real number system, which is abbreviated a lot of times with the script R for the real number system. And that's what we studied in calculus. The only thing really missing here is if you add imaginary numbers like the square root of -1, when you add those into the real number system, you get the complex numbers. And those are pretty much what everybody will study in any applied field. If you're super duper lucky, you might even take a complex analysis, which is calculus with complex numbers, where the square root of -1, the imaginary numbers are introduced. But okay, that was just a quick review. Sometimes when an idea comes up like this rational number, I just do a quick review just to make sure we're up to date. But this one, as I said, even if I never told you this theorem, you'd be able to see that this is going to be 0 just by thinking about what's going to happen as the denominator gets bigger and bigger. 1 divided by a bigger and bigger number would be approaching 0. And then the other part of this just says if r, positive r, is a rational number such that x to the r power is defined for all x, then, and notice that there's this little caveat here because now we've got negative numbers going under here. So if like r is 2 or is 1/2, like you're taking the square root of a negative number, then of course it's not going to be defined, right? But if it is defined, so we're doing something like this, so maybe r is the cubed root, right? You can have negative cubed roots. So then if it is defined, then we get the same thing here. We are going to get a 0. So the limit is still going to be 0. And then we've got example 4, a quick example of the theorem above. Again, even if I never mentioned that theorem, you would probably be able to see here that I can make this expression as close to 0 as I want to by making x large enough. But just a quick review of this graph, which you've all seen before, but you may have not seen it in a while. But that graph, if you were to graph that function, goes something like this. Of course, there's no negatives because we're going to square these numbers. And you can see that as x goes off to infinity, the function itself goes to 0. The limit of this is equal to 0, and that agrees with the theorem above. So the next topic we talk about is evaluating the limit at infinity or negative infinity of a rational function. But just before we get started, if you remember in section 2.3 we started seeing these indeterminate forms of 0 over 0. So today we're going to start seeing another indeterminate form of infinity over infinity. And we'll see that a lot when we look at these rational functions and we're taking these limits at infinity. So there's a technique. So if you remember when we had this indeterminate form 0 over 0, we would try, there's a little process we could go through to get it out of indeterminate form. We could try factoring, or we'd look and see if there was a radical. We would multiply by a conjugate, or we could try to combine like terms. And there were basically 3 techniques for dealing with this 0 over 0 indeterminate form. Infinity over infinity, or there could be plus or minus here or here, doesn't matter, but basically any sort of infinity over divided by another sort of infinity. For these, there's a go-to technique. So as over here, we had 3 different things to try. For this sort of indeterminate form, there's going to be basically one thing to try. So let's look at that next. So evaluating the limit at infinity or negative infinity of a rational function. So to do this, we first divide both the numerator and the denominator by the highest power of x that occurs in the denominator. And we can assume x is not equal to 0 since we're interested only in large or large negative values of x. We don't have to worry about dividing by 0 or anything. If you look at this first example, so we're taking the limit of this rational expression as x goes to infinity. So basically, as we plug in infinities up here, this term will dominate. We're going to have some sort of infinity cubed. So this numerator is going to be going to infinity. And same thing with the denominator. They're both going to infinity. So what we want to do, according to this, is we want to divide both the numerator and denominator by the highest power of x that occurs in the denominator. It's got to be the denominator. So in the denominator, the highest power of x that occurs is x cubed. So basically, we want to divide this whole numerator by x cubed and the whole denominator by x cubed. And the way we show that is we multiply by 1 in the form of 1 over x cubed divided by 1 over x cubed. And then, of course, this really, when I multiply, first I'm multiplying by 1 because numerator and denominator are the same. And then also, when I multiply by this, you could think of this thing as distributing through here. So multiplying by this in the numerator has the effect of dividing each term by x cubed, because multiplying by 1 over x cubed is equivalent to dividing by x cubed. And then the same thing down here. So that once we do this, if you think of this, kind of think of this as being, as if there were parentheses, we're going to distribute this through here. So what we'll end up with then, we'll get the limit as x approaches infinity, and we'll have 2x cubed over x cubed minus x squared over x cubed plus 8 over x cubed. And then in the denominator, we'll have 7x cubed over x cubed plus 4x squared over x cubed plus 7x over x cubed plus 1 over x cubed. And then we can go through and clean these up. So this is really just 2, right, because the x cubes will cancel. Here, this is equivalent to 1 over x. So if we clean all these up, this becomes the limit as x approaches infinity of 2 minus 1 over x plus 8 over x cubed. Down here we get 7 plus 4 over x plus 7 over x squared plus 1 over x cubed. And normally I might not even show this step. I'm just showing it now because it's our first time. But usually, once you do a few of these, you'll sort of automatically go from here to here. Now at this point, if you look at this, we are no longer in the indeterminate form. So I probably should have said at this point we had this indeterminate form, infinity over infinity. And when we're in this form, there's just a go-to technique that works on, that we'll pretty much try every time. So, which is right here. Divide both the numerator and denominator by the highest power of x that occurs in the denominator. So every time you see this, just do that. So we'll show that by multiplying by 1 in a form like this. That gets us to here, and now if we take the limit, we're going to get an answer. We're no longer in this form. So when I take the limit of this numerator, x is getting huge, right? So the 2 is just here. The 2 is not affected by this limit. But as this x goes towards infinity, I have 1 over a huge number. So I can make this be completely insignificant. So the numerator will be completely dominated by this 2. Because we can make x, as x gets bigger and bigger and bigger, these two terms become insignificant. So you can think of it like that, or you can use the theorem that we just talked about that said that the limit of this is going to be 0, limit of this is 0. But usually you just think, okay, as x becomes huge, this term is going to go to 0, and this term will go to 0. The denominator is very similar. 4 over x will go to 0, this goes to 0, this goes to 0. So what we're meaning is that we can make these terms be as close to 0 as we want, so that the only thing that really will be left of significance is 2 over 7. So when we take the limit of this last expression, we just get 2 over 7. So the limit of that is 2 over 7. And then you can make a little note here also, because of what we talked about earlier. So there's a horizontal asymptote also here. So I'm going to say y equals 2 over 7 is a horizontal asymptote. So if you were to graph this expression as you went out further and further to the right, got bigger and bigger values, this would be a horizontal asymptote. The line y equals 2/7. Remember, horizontal asymptotes are lines, so I need the y. It's a horizontal line, so I need y equals. So this wasn't part of the question. They just said take the limit. This is just a little extra, like geometrically, when I take the limit of this and I get 2/7, what that means is that the graph of this expression, if we were to graph it, it would have a horizontal asymptote of y equals 2/7. Example 6 asks us to find the horizontal and vertical asymptotes for the graph of this function. first we need to look at the square root of x squared. So if you think about the square root of x squared, here's a question. Is that equal to x? Is square root of x squared equal to x? Well, suppose x equals -3. Let's just suppose x equals -3. So if I put a -3 in here and square it and take the square root, will I get back a -3? And of course I won't, because as soon as you square it, you get a 9. So it turns out the square root of x squared is actually equal to the absolute value of x. And this is shown actually in the appendix in your book in page A7, the appendix A, page 7. And what you see is that since the square root of x squared equals the absolute value of x, it's basically because the square root of x squared is equal to x for positive values. All right, so if you plug a 5 in here, then it works. 5 is positive, but the square root of x squared is equal to -x for x less than 0. And so that's why it's equal to the absolute value of x. So all of this is basically saying that when you have the square root of x squared, it's equal to the absolute value of x. And then we talked about this earlier. The absolute value of x is actually a piecewise defined function. It's equal to x if x is greater than or equal to 0, and -x if x is less than 0. And the reason we just reviewed this will be pretty apparent in a couple of minutes here. When it comes to finding vertical asymptotes, there's really nothing new. You do exactly what you did in an algebra class. Just like in algebra, you just set the denominator equal to 0. So, for instance, for our problem here, if I want to find the vertical asymptotes of this expression, I'm going to take this denominator, set it equal to 0, just like we would have done in algebra. So we add 5 to each side, divide each side by 2, and we get x equals 5/2. And we can see that if we plug in 5/2 here, we're going to get division by 0. So that's a vertical asymptote. So if we were to graph this function, there'd be a vertical asymptote at x equals 5/2. So to find the vertical asymptote in calculus class, there's nothing new. You just find it the same way you did in algebra class. Now in calculus, you can show why this is true. So here's the why part. Now I typically don't ask you to do this next part, but if you were ever asked, here is why. So I'll just say here is why. And this is calculus. So if we take the limit as x approaches 5/2 from the right of our function 3x squared plus 2 under the radical over 2x minus 5. And if you think about what's happening here, the numerator is just some number. If I just plug in 5/2 or 2.5 here, square it, multiply by 3, add 2 and take the square root, this just gives me a number. This isn't really important, but the numerator is going to be some number around 4.6. Not really important. What's important is the denominator, because I know if I plug in 5/2, I'm going to get a 0 here. But we're approaching 5/2 from the right. So we're going to have numbers that are always bigger than 5/2. So I'm going to double it so that this will be a little bit bigger than 5, because I'm approaching 5/2 from the right. So it'll be a little bit bigger, but not much bigger than 5, so that as this gets closer and closer to 5/2 from the right, this is going to get closer and closer to 0. So I basically got some constant divided by 0, so that as a limit, the limit here, the limit of this would be infinity. Also, if we take the limit as x approaches 5/2 from the left of our expression, well, again, the numerator is going to be just some number, roughly 4.6. And the denominator, now this time I'm approaching 5/2 from the left, so I'm coming in from values less than 5/2. So when I double it, this is going to be a little bit less than 5. Really close to 5, but less than 5. So when I subtract 5, I'm going to get a really tiny but negative number. So I'll have a constant divided by a really tiny but negative number, a number approaching 0 through negative values, so that as a limit, this would be negative infinity. And this just basically shows that since the function approaches infinity as we approach from the right, approaches negative infinity as we approach from the left, that we're going to have a vertical asymptote at 5/2. So this is how you find it, nothing new. This is how you show it. Now, in my class, I'm just going to ask you to find it. You're not going to have to actually show it, but if you were asked to, this is how you would show that. Now, finding vertical asymptotes, we didn't have to do anything new. We just used algebra. But for horizontal asymptotes, we're going to have to use calculus here, because what we're going to do is we're going to use limits. So to find the horizontal asymptotes, we want to think like long term, what's going to happen to our function. So to do this, we can take the limit. So I'm going to look at the limit as x approaches infinity and also the limit as x approaches negative infinity. But for now, we'll just consider the limit as x approaches infinity. And you can see if I just plug in infinity, so to say, like think of as x approaches infinity, I'm going to get infinity on the top and also infinity on the bottom, right? Because 2x minus 5 as x approaches infinity, it's just going to be approaching infinity. So I've got infinity over infinity. So with this particular type of indeterminate form, there's a go-to method we use. And that method we just talked about is that we are going to divide the numerator and the denominator by the highest power that occurs in the denominator, which is just x to the first power. So basically what we have to do is multiply by 1 in the form of 1 over x divided by 1 over x. And this has the same effect as dividing the numerator and the denominator by x, which is the highest power in the denominator. So when we do this, in the denominator, this will distribute through, so this is not really a problem. But over here, we're going to have to do something different because we've got a radical here. So the first step is going to be the limit as x approaches infinity, and we have 1 over x times this radical 3x squared plus 2. Now the denominator is not really a problem. We can distribute this through here, right, and we will get 2x over x minus 5 over x. So the problem is right here, right? So if I have a problem like this, if I have 5 times the square root of 3x plus 1, can I just multiply the 5 through and get 15x plus 5? Is that true? And of course, when you look at that, you should be saying absolutely not. Think about it. Let's say you're going on a date, and the date goes great. You know how it is. You go to a math seminar, maybe go out to dinner, and everything's going great. You drop off your date at home, and your date's like, hey, want to come up and do some calculus homework? And you're like, I sure would. And you go up there, you're working on some homework, and let's say your date, it's been going so well, and your date says, here's my answer, but I'm going to simplify it to this. Want to go on another date? What are you going to say? I know what you're going to say. You're going to say, absolutely not. This date is over, right? We can't be doing this kind of nonsense. So if there's a radical here and a number out front, we can't just multiply it through there. But we do know this. Isn't it true that the square root of a times the square root of b is equal to the square root of a times b? So what we're going to have to do is somehow put this under a radical. So here's where what we talked about earlier with the square root of x squared is going to come into play. So over here, x is approaching positive values, right? X is approaching infinity, but is always positive values. So if you think about what we wrote before, we had x squared equals the absolute value of x, which is equal to x if x is greater than or equal to 0, negative x if x is less than 0. For us, x is approaching infinity through positive values, so we are on this branch. And on this branch right here, we can see that x is the square root of x squared on this branch, right? Where we are at, x is approaching infinity, only positive values, right? So we're here, so that x is exactly the same as the square root of x squared. So what we could do then, if I have 1 over x, that is the same as 1 over the square root of x squared. And of course that is the same as the square root of 1 over the square root of x squared, which is the same as 1 over x squared, all under the radical. So what we're going to do is swap this for this. So what we'll do is we'll say this is equal to the limit as x approaches infinity of 1 over x squared under the radical times this radical, 3x squared plus 2, all over, and I can clean this up now and get 2 minus 5x. But from here, since these are both under a radical, now we can multiply these together and keep them under the radical. So we could write this as the limit as x approaches infinity, and then we'll have 1 over x squared times 3x squared plus 2. And you could do that in one step if you wanted to. I'm just trying to make everything really clear, so I'm going to keep it like this, and now I'll distribute this through. So this would give us the limit as x approaches infinity of 3x squared over x squared plus 2 over x squared under the radical. On the bottom we get 2 minus 5 over x. And then of course we can clean up the numerator. Get the limit as x approaches infinity of 3 plus 2 over x squared under the radical, and the denominator 2 minus 5 over x. Okay, at this point we can take the limit, because as x approaches infinity, this term will go to 0, this term will go to 0. In other words, we can make these terms as close to 0 as we want just by making x large enough. Right, so as a limit, that will go to 0, this term goes to 0, and what we're left with then is just the square root of 3 over 2. So the limit of that expression is the square root of 3 over 2, which means that the line, so here's what we can say, the line, remember it's the horizontal asymptote is a line, y equals the square root of 3 over 2 is a horizontal asymptote of the graph. Of f of x. So we considered x approaching infinity. What we also have to consider is x approaching negative infinity. Now the thing to remember about this though, as x approaches negative infinity, then as x approaches negative infinity, our x values are going to be less than 0. So as x approaches negative infinity, we're over here. When we're on this side, we're over here. When x is approaching negative infinity, x is always less than 0. So in that case, negative x is equal to the square root of x squared. And that will come into play when we do the next part. So we're going to basically do the same thing we did, but this time we're going to approach negative infinity. So we will have the limit as x approaches negative infinity of our expression. So same expression as before, 3x squared plus 2 under the radical, 2x minus 5. And I'll go a little faster here because it's going to be very similar. The only difference is we're going to have to deal with a negative. It's a little bit more work. But still, when we take the limit at this point, we're going to get infinity on top, negative infinity on the bottom. So we've got an indeterminate form, infinity over negative infinity. Remember, this infinity over infinity form, the signs don't matter. It's still an indeterminate form that we have to figure out. And any type of infinity over infinity, regardless of the signs, we have the go-to method. It says divide each term in the numerator and each term in the denominator by the highest power of x in the denominator. So again, the highest power of x in the denominator is just x to the 1. So we multiply by 1 in the form of 1 over x over 1 over x. And just like before, we get the limit of x approaching, of course, negative infinity this time. We get 1 over x here, 3x squared plus 2 in the numerator. The denominator, we can actually just distribute that through and get 2 minus 5 over x, just like before. But now here's where it's going to be different. Okay, so since x is approaching negative infinity, like we talked about just a minute ago, since x is approaching negative infinity, then we know that negative x is the same as the square root of x squared. Okay, doesn't that mean that x equals negative the square root of x squared? So that 1 over x is going to be negative 1 over the square root of x squared. Right, so we know this is true because x is approaching negative infinity, and we talked about that before. This thing is a piecewise defined function because it's equal to the absolute value of x. So in this case, this is equal to negative x. And so I just took this equation, multiplied each side by a negative 1 to get here. And then I just took the reciprocal of each side to get here. And then, of course, that is equal to negative square root of 1 over the square root of x squared, which is equal to negative 1 over the square root of x squared. And of course, the negative has to stay outside of the radical always, right? It's not under there, it's outside in front. So then what we're going to do is replace the 1 over x and our limit above with this here. So that will give us the limit as x approaches negative infinity, negative 1 over x squared out here, times 3x squared plus 2. Down here we've got 2 minus 5 over x. And then we're going to just distribute this through. And since we've already seen this, I'm going to skip some of the steps here. But that will give us the limit as x approaches negative infinity. So when we distribute that through, now look at the negative here is out front, right? It's going to just stay there in front of this this term, or the result we're going to get when we multiply. So we will have negative, and once we clean that up, 3x squared over x squared is just going to be 3 plus 2 over x squared. Oops, that's a square root. And here we get 2 minus 5 over x. All right, so at this point, we can take the limit. So as x approaches negative infinity, this will still go to 0. This will also go to 0, right? We can make both of those terms as close to 0 as we want. That goes to 0. That term goes to 0. And the limiting value then is negative square root of 3 over 2. Okay, so that means that the line, again, it's a line, it's a horizontal line, y equals negative square root of 3 over 2 is also a horizontal asymptote of the graph of f of x. Okay, so this graph has two horizontal asymptotes. Let's take a closer look at these horizontal asymptotes. There are many ways for the graph of a function to approach the line y equals L. This line is called the horizontal asymptote. Remember, I know I keep stressing this, but it's because details really matter. A horizontal asymptote is a line, right? It's going to look like y equals L, where L is just some number. Here are a few of them here. So, the first case, we've got this line y equals L, and maybe the maybe the graph of the function goes something like this, and it crosses it and then comes back down and gets closer and closer and closer, but never touches. So in this case, we can see that the graph of the function crosses the horizontal asymptote once. Okay, so the graph can cross the horizontal asymptote. Okay, but it could also do something like this. Maybe the graph of the function does this and never touches it, and so it never crosses. So in this case, the graph never crosses. Never crosses the horizontal asymptote. Okay, that happens too sometimes. What you could have is something like this, where the graph of this function, it crosses infinitely many times. It's getting closer and closer and closer. It's hard to show on a graph by hand like this, but think of this, it gets closer and closer and closer, but it crosses infinitely many times. So that could also happen. With horizontal asymptotes, all of those things are possible. The graph could cross the horizontal asymptote once, it could never cross it, could cross it infinitely many times. But the graph of a function can have is a total number of these horizontal asymptotes. Like this picture, there's just one of them here, there's one of them here, and there's one of them here. But a graph of a function can have either 0, 1, or 2 horizontal asymptotes. But the graph of a function never crosses a vertical asymptote. So it will never cross a vertical asymptote. Now it can do something like, we've all seen graphs like this that sort of jump through one. So let's say we've got these asymptotes here. So we can have a graph that goes like this, and then maybe like this, and something like this. So it can like jump here, but you'll never have a graph where the graph actually goes through and cuts through. It won't cut through this asymptote. So the graph of a function never crosses a vertical asymptote, like never crosses through it. It can like jump over it like this, but it won't actually cross through it. Where it can with a horizontal asymptote, as we saw above, the graphs can cross horizontal asymptotes. For example 7, we are asked to find the limit or show that it does not exist. So if you look at the first one here, the limit as x approaches negative infinity of x cubed. Well, just think about what's happening here. If you just think of plugging large negative numbers here and then cubing them, they just get more large, right, and negative. So the limit of this is just negative infinity, right? There's nothing really tricky here. Think of it as putting giant numbers in here that are negative, and we cube them, they just become more giant negative, right? So the limit of this is just negative infinity. And likewise over here, the limit of the square root of x as x approaches infinity is just also going to be infinity, right? We could make this expression, the square root of x, we can make that as large as we want just by making x big enough. So the limit of that expression is infinity. We'll have a little problem with this next one though. This, if I plug in infinity, I'm going to get infinity squared, which is infinity minus infinity. So we actually have right here, we have another indeterminate form. This is infinity minus infinity. And you could make the argument that, well, this one is x squared, so it's bigger than this one. So this is maybe going to be a big infinity minus a small infinity. So maybe it's going to be 0, but we don't want to use that kind of argument. This is just, especially when these get more complicated. So we want to have a better way to do this. So it's basically infinity minus infinity. That's the indeterminate form, but it's really easy to fix. We can put this into a different form that's not indeterminate. What we could do is just think, what if we factor an x out of here? So isn't it true that this is the limit as x approaches infinity of x times x minus 1? Now in this case, as x approaches infinity, this is infinity, and infinity minus 1 is still infinity. So this is really just infinity times infinity. And infinity times infinity, that is not indeterminate, right? Think if you take a huge number, multiply it by another huge number, you're never going to go like, oh, look at that, it's 4, right? It's going to be an even more huge number. So the limit of this is just infinity. So what we did is we took indeterminate form, infinity minus infinity. This indeterminate form could be absolutely anything. Functions that are approaching infinity minus other functions that are approaching infinity could be anything. And we don't want to try to argue through this with words, right? This is so much easier. Fact out in x, now we've got infinity times infinity. That is not indeterminate, that is always infinity. Okay, so with that in mind, looking at this one and seeing we've still got this indeterminate form, why don't you press pause a second and try this one out and then check back. No, really, press pause, try it, and then check back. Okay, so hopefully you press pause, did this on your own. Remember, the only way to learn this is to work through these on your own. So this one, to get out of our indeterminate form, we could once again factor. We could say, let's take the limit as x approaches infinity and factor out an x squared, and then we're going to get 1 minus x. And then now we've got, plug in infinity, we've got infinity here. 1 minus infinity, well that's negative infinity. So this form is really, well, let me do this in red to be consistent. This form is really going to be infinity times negative infinity, right? You've got infinity, because we're squaring infinity, and then 1 minus infinity is negative infinity. Well, positive times negative is negative, so the answer to this is just negative infinity. Okay, and there's actually going to be, I'll just give you kind of a heads up for what we're going to see. We're going to see 7 indeterminate forms. We've seen this one. We've seen this one. Another one we're going to see is 0 times infinity. And we've also seen this one, infinity minus infinity. There's other ones that are a little trickier to use that have power. So 0 to the 0, 1 to the infinity, and infinity to the 0. These are the 7 that we'll see. And remember, these are not numbers. These are functions approaching these things. So this would be an example, would be a function approaching 1, and at the same time, that function that's approaching 1 is being raised to the power that's approaching infinity. Right? So these are all indeterminate forms. They could be literally anything just based on what the particular functions are. All right, so we will see all of these soon enough. But for right now, let's consider this. The limit as x approaches infinity of cosine of x. Now, cosine of x, we know what that does. Cosine of x just does this forever, right? It oscillates forever. So with something like this, as you go further out to infinity, nothing changes. It keeps on oscillating. And the key is it never approaches any one number. So because of that, the limit as x approaches infinity of cosine of x does not exist. The reason it does not exist is that it never approaches any one number. And for a limit to exist, it has to actually approach a number L, right? Where this one, it just oscillates forever, never approaching any one number, so the limit does not exist. All right, let's try this next one. Letter F, we've got a limit as x approaches infinity. We've got infinity to the, well, we've got x to the 4th plus x over here, so this numerator is going to approach infinity. The denominator, though, is going to be approaching negative infinity. So we've got the infinity divided by negative infinity. And again, with this one, it's any signs don't matter. It's infinity divided by infinity. So we have a go-to method where we are going to divide the numerator and the denominator by the highest power of x in the denominator, which is just x. So the way we signify that is we multiply by 1 in the form of 1 over x over 1 over x. Once this distributes through here, we end up with the limit as x approaches infinity. So the numerator is going to be x cubed plus 1. Denominator is going to be 5 over x minus 1, right? And that's just from distributing these through and then cleaning them up. So up here, we can see the numerator is basically just going to grow without bound, as large as you want. The limit of the numerator is going to be infinity. Now the denominator, on the other hand, we can see that this 5 over x term will go to 0. So we are essentially going to have infinity divided by negative 1. So the limiting value of this is going to be negative infinity, right? We've got a positive divided by negative. So the limit of this expression as x approaches infinity is negative infinity. And then it looks like we saved the best for last. So if you look at this one, we've got the limit as x approaches negative infinity. So in here we basically have a negative infinity plus, now under here we're going to square this infinity. So this would be sort of like an infinity minus infinity, or you could think of it, well, this is going to be a bigger infinity. So essentially we would have like a negative infinity plus infinity, which is the same as infinity minus infinity, which is indeterminate form. But anyway, we've got something strange happening here, and the way to get out of this is going to be similar to what we did in section 2.3 when we had radicals, and we would think of a conjugate. So when you get something like this with a radical again, we can think of this as, let's think of this as if this were over a 1. And then think of the conjugate, just like before. So I'm going to go x minus the square root of x squared plus 2x, and then over itself here. And then we're going to multiply the conjugates together, because the nice thing about this, again, is the outside term and the inside term always cancel. So once we do this, we'll end up with the limit as x approaches negative infinity. So the numerator, we're going to have x squared minus x squared plus 2x. The denominator, just like before, we don't want to, the non-conjugate pair, we don't want to expand them. We just want to keep them how they are. Now in this case, it's just a 1, so it doesn't really matter. But if it were something else here, we do the same thing as before. We don't like distribute those through. So this denominator is just going to be x minus x squared plus 2x under the radical. And then we can see at the numerator right here, this one can clean up. It's really x squared minus 2x. So x squared minus x squared is gone. So what we'll have is a limit as x approaches negative infinity. And we're going to have a negative 2x in the numerator. And down here we've got x minus x squared plus 2x. All right, so if we go to take the limit at this point, we're going to have an infinity up here, right? Because this is negative infinity. Negative 2 times negative infinity would be infinity up here. Here we're going to have minus infinity, essentially minus another infinity. Like minus 2 infinity, which is like negative infinity. So we've sort of got this infinity over infinity. So we can do what we did before. We can think of multiplying by the highest power of x in the denominator, which would be 1 over x. 1 over x divided by 1 over x. And then we'll just multiply through here. So we will get the limit as x approaches negative infinity. So in the numerator, we're just going to have a negative 2. In the denominator, so in the denominator, we're going to treat this, it's 2 terms, so I'm going to distribute this through. And what we'll get is 1 minus, now I've got this 1 over x times x squared plus 2x. Got that same situation where I need to get this in here. But now I'm approaching, x is approaching a negative infinity, not the best not a sketch here, but it's a negative infinity. So now we're on the branch. Remember when x is less than 0, just a little recall here. The square root of x squared equals negative x when x is less than 0. And x is definitely less than 0, right? X is approaching negative infinity. So over here, these are equivalent. So if I have 1 over x, just like before, I'm going to have negative 1 over the square root of x squared, or negative square root 1 over x squared, just like we did before. Same idea. So I can replace this with this. I've already got a minus here, so I'm going to put another minus. So we'll get minus minus, which will actually make a plus. So we have the limit as x approaches negative infinity, and the numerator is negative 2. The denominator will be 1 plus, right? It's a plus because there's a minus here, but then when I swap this out, I basically swap 1 over x and then put in its place negative 1 over x squared. So we get minus minus, which makes this plus. And then we will get, if I distribute that through, maybe I'll do it like this first. Let me do it in 2 steps. This will be here along with x squared plus 2x. Then I can distribute that through and we'll get the limit as x approaches negative infinity. Negative 2 here, we get 1 plus. So when I distribute here, I'm going to get the radical here. I'll get 1 plus 2 over x. And now we can take the limit. This term goes to 0. And we'll get negative 2 over 1 plus the square root of negative 1. And I know you guys would never leave it like that, right? You'd never do that. Because that is negative 2 over 1 plus 1, which is 2, which gives us negative 1. So, letter G, the answer to this limit, a lot going on here. This is not a typical problem. It's one of the trickier ones, but you'll see them occasionally. The answer to this limit is negative 1. So that should take you through everything you need to know to get started about limits at infinity and horizontal asymptotes from section 2.6. So of course, you know the only way to get good at this stuff is to do the homework. So try the homework, and if you have any questions, let me know, and I will talk to you soon.